So in the last session, we started the session by discussing about NSM FRP strengthening. In this, we saw how NSM strengthening works, different designs for NSM strengthening, and saw few literature studies in which different factors affecting NSM strengthening, NSM FRP strengthening was done. Then we talked about strengthening of beam column joint using FRP. Here, we talked about how beam column becomes critical, particularly in earthquake prone areas where lateral stresses becomes critical. We saw a couple of literature, saw different arrangements of FRP joint strengthening, and talked about hysteresis loop and behavior of loading and unloading. Then we talked about different modes of FRP debonding failure near the end, flexure failure, shear failure, and concrete crushing. We then saw different anchorage systems. Those were of three types: type 1, type 2, and type 3. And then we talked about different anchorage devices. Main highlights were the FRP strips, metallic strip anchors, pi anchors, and NSM anchors, as you can see in the images also. Then we talked about the FRP design consideration. We talked about three factors for design considerations of FRP: strengthening limit, which decide whether the existing structure has sufficient strength or not for undergoing retrofitting. Second was strength and serviceability requirement, in which we looked into strength and load factor of structural component. And third was FRP strength reduction factor, which is used for accompanying the uncertainty associated with the inherent FRP system. Accordingly, we saw how different FRP compares on different parameters and solved a case study to make a choice of FRP strengthening. Finally, we talked how FRP installation is done in a step-by-step manner. So first is the preparation of concrete surface, where concrete uniformity, surface uniformity and surface flatness plays an important role. Then second was checking the tensile strength of substrate using pull-out testing. Third was addressing the environmental condition like presence of moisture and temperature, which can affect bonding or pot life of the FRP. Fourth was setting out exact location where FRP needs to be installed, then applying FRP, and finally checking the FRP for its quality and suggesting or implementing repair if needed. Okay, so the discussion till now we had on FRP strengthening, we saw how FRP is installed, what FRP is, how FRP strengthening how FRP strengthens different member for different requirement, how to make choice of FRP and how to install FRP. Today we will see how FRP is designed based on requirement. So we know FRP strengthening can be carried out either for flexural strengthening or shear strengthening or axial strengthening. Okay, so let's look at designing FRP for each of them one by one. So first we have a design approach of FRP retrofitted flexure member. Okay, and the aim here is to evaluate whether the choice and extent of FRP retrofitting design meets the requirement of FRP strengthening or not. Okay, now there is a basic rule of strengthening that is shown in the equation here. That is, the strength after retrofitting should be more than the strength required. Okay, so here we have different parameters. Phi is the strength reduction factor, which takes into account the durability and environmental factor that we discussed last week when we talked about different criteria of strengthening. Mn is the nominal strength of member after retrofitting. So after applying FRP, what is the strength of the member? That is noted by Mn. And Mu is the required strength of member post load increment or functionality change. So Mu is the strength that we require from the member. So suppose I have a beam. Okay, initially it was supporting 100 kilonewton of load. Now I want to strengthen the beam till 150 kilonewton. So my 150 kilonewton will be my Mu, the required strength of the member. Okay, so what is known to us? We know how much load is increased on the structure, that is Mu. And what needs to be estimated? Is the choice of FRP material and the extent of retrofitting is sufficient to meet the strength demand or not? So suppose we have chosen a particular FRP. Now we need to check whether that particular FRP that we have chosen is sufficient or not. And for that we need to determine MN value. Okay. Now, how to decide the value of strength reduction factor? So it depends upon the strain at nominal strength and the type of the member. So here epsilon T is the net tensile strain in extreme tension steel at nominal strength, and epsilon SY is the strain corresponding to yield strength of steel reinforcement. So if we know the value of these two quantity, epsilon T and epsilon SY, so depending upon the type of member, whether it is a ductile section or a brittle section or an intermediate section, we can decide what will be my strength reduction factor associated with the design of FRP. Okay, and this generally varies in a linear range from 0.65 to zero point 0.9 based on the value of epsilon T, that is the net tensile strength in extreme tension steel at nominal strength. Okay, so we'll see later on how we determine these value epsilon T and epsilon SY and how we use this graph. Okay, the most important thing, or we can say assumption in design of flexure, is the strain compatibility. As we you may know from the designing of reinforced concrete also from IS 456. So what does strain compatibility mean? So at a particular section of in the member, the strain experienced by different materials are the same. So suppose I have a beam, okay, and I am taking this section, okay, so there can be steel here, there can be concrete here, and there can be steel and concrete are here. Okay, suppose there are steel and concrete both, so the strain experienced by both steel and concrete will be the same. That is known as strain compatibility. Okay, so there is proper bonding between the concrete and the steel so that the stress transfer is uniform and the strain experienced by both the members are the same. That is the major assumption that we make in while designing for a flexure member. Okay, how this is important here? Because strain in a retrofitted RC member can be different based on the different possible failure limits of concrete, steel or FRP. Okay, so based on strain value, we'll be able to design and dictate the failure mode. Okay, so if there is concrete crushing, the compressive strain in concrete at extreme end is given by this value. Epsilon C is equal to 0.003, where epsilon C is the ultimate tensile strength of unconfined concrete. If there is rupture in FRP, the tensile strength in FRP reaches the extreme strain, and it is given by epsilon FU, which is nothing but the ultimate rupture strain of FRP. And there can be debonding in of FRP, where debonding strain of FRP is given by this equation. Epsilon FD is equal to 0.41 times square root of FC dash upon N EFTF should be less than zero point 0.9 times epsilon FU. And there the terms are basic terms are clear to epsilon FC dash compressive strength of concrete, N is the number of FRP piles, EF is the elastic modulus, and TF is the thickness of FRP pile. Okay, so based on the strain value that we are getting, we will be able to design and dictate the failure mode also. Okay, how we will see its application when we will do the numerical. For now, just try and remember these three conditions. There can be concrete crushing, there can be rupture of FRP, and there can be debonding of FRP. Its application we will see later on. If does someone has any doubt, please mute yourself. Mr. Shahid, please mute yourself if you don't have any doubt. Okay. Now, before going into flexure design or understanding how we design a FRP section for flexure, let's look at different assumptions that we should consider before designing. So, assumptions for design of FRP strengthening are Design calculations should be made based on dimension, internal reinforcing steel arrangement, and material properties. So when we are designing a FRP retrofitted flexure member, we should consider the dimension, the internal reinforcing steel arrangement, and the material property of existing member also that needs to be strengthened. Plain section before loading remains plain after loading. Okay, this is loading. Okay, so this is very basic assumptions that has been carried on from the IS 456 design. There is no relative slip between FRP and concrete, so that there is strain compatibility between them. Shear deformation within adhesive layer is neglected. So when we are talking about FRP, externally bonded FRP, we use certain adhesive to bind these FRP to the concrete, right? To the infrastructure, and we are neglecting any kind of shear deformation within the adhesive for the design purpose. The tensile strength of concrete is neglected, which is very common. The tensile load will be taken by either steel or FRP. Maximum compressive strain in concrete is taken as 0.003. So this is a fixed value that we are assuming. And FRP reinforcement has a linear elastic stress strain relation that is known to us from the start of the discussion of FRP. Okay. So, as we saw earlier, also when we talked about FRP strengthening for flexure, when there is a beam having an FRP retrofitting, the strain diagram of the beam gets an additional component of FRP as well as the stress component. Okay. So in strain diagram, there are two basic strain bearing elements. First is the epsilon Cu, that is for concrete top fiber, and second is epsilon S, that is for steel reinforcement. We know their meaning: the strain in concrete at ultimate loading and the strain in steel. Okay, here epsilon Fe is the strain in FRP due to the loading action. So once we apply an FRP sheet, there is an additional member which will take the strain, that is the FRP element, and that strain is denoted by epsilon Fe, and it is given by this equation. And while epsilon Bi is the strain in concrete at the time of FRP installation. Okay, why these two terms are added here? So, because when we install a FRP, suppose we are installing a FRP at the base of a beam, the bottom face of the beam would be under some strain initially before installation of FRP, which is needed to be taken into consideration for designing of FRP. Okay, thus the total strain at the bottom fiber is written as epsilon Fe plus epsilon Bi, and this Bi is the strain in the concrete before the installation of FRP. Okay, in the stress diagram, we can see above neutral axis, we have the concrete stress block that is taking compression. This block is usually parabolic, but for simplicity in design, we can convert it into a rectangular block with the side alpha times alpha 1 times fc dash and the width beta 1 times c. So here alpha 1 is the multiplier factor for converting the non-linear stress into an equivalent rectangular block. So from this to this, it is the conversion factor. Okay, and beta 1 is the ratio of equivalent stress block to the depth of neutral axis. So this is my depth of neutral axis, which is denoted by c, and there is some proportion after conversion till which my compressive stress block will be present, and that is denoted by beta 1 times c. Okay, and below neutral axis we have steel that is taking compression, that is taking tension, and we have FRP that is taking tension. So this FRP is the element which is contributing in the additional tensile load carrying capacity of the member. Okay, so by simplify now in strain diagram, by just simplifying, simply by using the equivalent triangle concept, we can determine the relationship between strain in FRP, which shall be less than the demanding strain if we are assuming a barren section. Okay, so we can write strain in FRP just by solving this similar triangle theory, where we say epsilon cu upon c is equal to epsilon fe plus epsilon bi upon this length. Okay, this length will be nothing but df minus c. Okay, so you can see here the similar equation is written and rearranged. Okay, and this should be less than epsilon fd, which is the debonding strain if we are assuming a balanced section design. And stress in FRP we can simply write as the modulus of elasticity of fiber that will be known to us of FRP, and the strain in FRP that we will calculate from the first equation. Okay. Similarly, for steel also we can determine the stress and strain equations. So strain in steel will be again determined by the similar triangle concept, and stress can be written as modulus of elasticity into strain. Okay, this should be less than Fy because this is the yield strength of steel. And in concrete also epsilon Cu is fixed for us, and stress in concrete can be determined by this stress block. So length into breadth into FCK, that will give me the stress in the concrete. Okay. So by simply equating the forces, the total compression force must be equal to the total tension force. We can determine the value of depth of neutral axis because everything else will be known to us. It is just the depth of neutral axis that won't be known to us. So we can determine that value from just equating the forces. And once we have equated the forces, we can determine the nominal moment capacity of the member, which will be nothing but the moment offered by the steel plus the moment offered by the FRP times the lever arm distance. So here you can see the same thing is written. So for steel, my lever arm distance will be different. For FRP, my lever arm distance will be different. So you can see both the terms are different. And the first part is just the force provided by the steel and resistance for provided by the FRP. Okay, so my total Mn can be written as Mns, that is the moment capacity of steel plus gamma f times mnf, that is the moment capacity of FRP, and this factor is denoting the durability reduction factor that we talked in the last session. Due to environmental condition, how my FRP performance can be affected. So for this we have defined this additional factor. Okay. And later on we can check for the serviceability conditions also. So for stress and reinforcing steel should be less than zero point 0.8 times Fy. Okay, and for determining this FSS, we at service load we can use this equation, and in compressive strength in concrete this equation is followed. Now this is not very major to us because if we opt for IS 456 design criteria, our serviceability condition will be the deflection. That deflection should be less than some value. So that can be done simply as we do in RC design. So won't give much emphasis to these criteria here. The important thing for us is the design of FRP, the choice of the material, and how that choice of material is able to take the required increment in load. Okay. So just to see how all these formulas are applied and how the concept works, let's see a numerical. Okay, that will go from scratch. Okay. So this is the question. A simply supported RC beam supporting a bridge deck will start experiencing 50% increment in live load. Okay. The consultant is asked to design the beam for FRP retrofitting, assuming that the shear strength is sufficient to meet the requirement, while the flexure strength, however, needs to be taken care of. So in the question, it is given that 50% increment in live load is happening. The shear strength of the structure is sufficient. We don't need to worry about that. We need to worry about the flexure strength, and for that we need to design the FRP retrofitting. Okay, so we need to design FRP for flexure strengthening of the beam. And these are the detail of the beam. It is a 5-meter beam. Width of the beam is 300 mm. Total depth is 600 mm. Compressive strength of concrete used in beam is 30 MPa. Steel tensile strength is 415 MPa. For initial reinforcement, 5 number of 20 dia bars are provided, and the existing moment capacity of the beam was 90 kilonewton per meter. And we need to design a FRP, CFRP sheet, which is used as an external FRP retrofitting, such that it can sustain 50% increment in live load. Okay, and these are the detail of the CFRP element: the thickness, the tensile strength, the rupture strain, and the modulus of elasticity. Okay, I will take a break of like a couple of minutes. Just try to understand this question. What all things are given. try to think about how you will proceed on with the question, and then I will tell the solution. Okay, just think about the question. In the meantime, if anyone has any doubt related to flexural strengthening using FRP, they can post their queries in the chat box. So we will look at that also. Okay, let's see the solution now. Okay, so what all things were given to us in the question? So we know that total 50% increment is live load is happening. We know the details of the beam, length, width, depth, compressive strength of concrete, tensile strength of steel, number of rebars that were provided, and the existing moment capacity of the beam. Okay, and we know the properties of CFRP also. And there it is mentioned the clear cover, okay, and the depth and the live load that is acting on the beam. Okay, so the first step is the load calculation because we need to know how much increment in moment capacity that is going to happen. So for that we need to determine the loads also first. So the dead load is nothing but the density into volume of the existing beam. Okay, it can be given as density of reinforced concrete is generally assumed at 2500 kilonewton per meter cube into volume, length into breadth into height. Okay, so 5 into zero point 0.3 into zero point 0.6. So this will give me the dead weight as 4.41 Newton per mm. Okay, so per meter length. So if I remove 5, so per meter length, what is the dead load? So this is the dead load, 4.41 Newton per mm. Okay, live load initially it is 10 kilonewton per meter, so it can be written as 10 Newton per mm so that I can get all the values in the same units. And after increment, 50% increment, my live load will become 15 kilonewton per mm. Okay, so initially my unfactored load is what? Dead load plus live load. So we can say it is 4.41 plus 10, so it will be 14.41 Newton per mm. Okay, and after load increment, it will become 15 plus 4.41, so 19.41 Newton per mm. Okay, second is the unstrengthened load limit. So we saw in the last live session that the initial beam should have a certain strength limit so that it can be retrofitted or not. So for that we need to calculate the unstrengthened load limit, which is given by 1.1 times dead load plus 0.75 times live load. Okay, but since this question talks about a bridge deck, okay, my bridge deck will continuously experience live load. So we saw in the last session also. So for cases where live load will be continuously acting, we should take the factor of 1. So instead of 0.75, I took the factor of 1 in this question. Okay, so considering this factor, my unstrengthened load limit post load increment will be 19.85 Newton per millimeter. Now I can calculate factored load simply by taking the factors as per IS code. So it will come out to be 21.29 before strengthening and before load increment and 29.29 after load increment. We can calculate the service load movement based on this unfactored load. It will come out to be this value. So WL square by 8 is nothing but the moment at the midspan due to continuous loading. So it is like expected that everyone knows how to calculate these moments and everything, because you may be given a point load or load at some arbitrary position. You should know how you calculate the moment so that you can do this initial step. So for continuous uniformly loaded beam, this midspan moment is given by WL square by 8. Okay, so service load moment will be these two values before and after load increment. Unstrengthened moment for this case will be 62.02 kilonewton meter, and factored load moment will be 65.52 initially, and after load increment it is 91.55. Okay, so this is the amount of moment that is required for us to be resisted after FRP retrofitting. Okay, initially we have been given that the existing moment capacity of the beam is 90 kilonewton meter. We need to increase it by 1.155 kilonewton meter. Okay, so since existing moment capacity is greater than the unstrengthened moment capacity, okay, we can say that the structure is suitable for undergoing the strengthening activity. So we saw this rule in the last session that the unstrengthened capacity of the beam should be more than the existing capacity. So since here it is following that condition, then we can say that the system is suitable for retrofitting activity. Okay. Now, first step is determining the material degradation parameters for FRP. Now, since this is a bridge deck will be exposed to the exterior environment, my environmental factor for CFRP will be 0.85. Okay, we saw in the last session also a table where different environmental factor values were given based on the exposure conditions. So for CFRP, that factor is 0.85. So we will decrease, we will multiply both the ultimate strength and the ultimate strain of FRP by this factor 0.85, and we will get these values. Okay, now I need to design my CFRP. So let's make a choice of one CFRP strip. Suppose I am providing a single strip of CFRP for strengthening. Okay, so my area of FRP will be nothing but number of strips n times thickness of strip, that is TF, that is given to me 2 mm, and the width of the beam. Okay, my width of the beam is 300 mm. So I'm completely attaching my CFRV on the base. Okay, so this will be 300. So my total area of CFRV strip is 600 millimeters square. This is my first step, that I have determined the material degradation factor and I have chosen one design of CFRP. Now second step is determining the existing material properties which are still unknown to us. So what is unknown to us? The concrete elastic modulus we still don't know. So the concrete elastic modulus as per IAS 456, it is nothing but 5000 under root FCK. So EC, the modulus of elasticity of concrete, is nothing but 5000 under root FCK. Okay, so that will be 2000 27,386 Newton per mm square. Okay, area of steel reinforcement we can calculate since we know the number of rebars that we have provided. So it will be nothing but 5 times the pi r square. So pi 3.14 into 20 mm dia, so 10 mm radius. So it will come out to be 1500 and 70 mm square. That is my area of steel. Now the total depth of beam is 600 mm. So the effective depth will be nothing but total depth df minus cover, cover is 40 mm, and the diameter by 2. Okay, so diameter is 20, so diameter by 2 will be nothing but 10. Okay, so my effective depth will be 550 mm. Okay, now, step 3 is to determine the existing state of strain at the bottom. Okay, why we need this? So that we can determine the strain in FRP, F epsilon Fi that we saw earlier. Okay, so for determining this, I need to first calculate the epsilon Bi value also. And how to determine this epsilon Bi, we will look here. Okay, so assuming that the beam is cracked, okay, before installation of FRP, suppose my beam is cracked due to load, okay, and the total load is still acting on the structure since the structure is not been asked to endure by retrofitting work. So since it is a bridge structure, it is not always possible that we can stop the flow of vehicles on the top of the bridge. The consultant is asked to repair the bridge while keeping the bridge in active state. So the total load that is acting on the bridge is still acting on the bridge. So assuming these two conditions, we can say epsilon Bi is given by this equation: mu times df minus kd upon ICR times EC. So ICR is the angular inertia of the cracked section, and EC is the concrete modulus of elasticity. Mu we know. Okay, we calculated in the before step 1. Df we know, d we know. We need to calculate ICR and we need to calculate k. K is the neutral axis depth. Okay, so you can see in this figure, this is my beam. Okay, it has a width B and effective depth H. Okay, and the area of steel reinforcement I know. Okay, so for determining K, the moment due to compression will be equal to the moment due to tension at a particular axis. So suppose along neutral axis I am calculating the moment. Okay, so due to this concrete block, which will be completely acting as compression, and in tension, I won't assume any concrete to be supporting the tension load. So the moment due to this concrete block will be nothing but EC times B times KD by 2. So B times KD is nothing but the area of concrete, effective area of concrete under compression, and KD by 2 is the distance of the center of mass of this concrete block from the neutral axis. So this is given by this equation. Similarly, steel we can write ES times AS time D minus KD by 2. So D is the effective depth. Okay, D minus KD is the distance from the neutral axis. So I can write the moment due to tension like this. Now here we know EC, we know ES, we know AS, we know D, and we know B. Okay, only thing that is unknown to us is the KD. Okay, so upon solving this equation, you will see it will be a quadratic equation. So upon solving, you will get the value of K as 0.31. Okay, once we know the value of K, just we need to determine the inertia of cracked section. So the inertia of cracked section is given by this relationship. Okay, you can remember this relationship also, or you can derive this relationship also when it is needed. So it is given by B times KD cube by 3 plus N times AS times D minus KD square. Okay, we know all the value B, K, D, N and AS. Okay, so just substituting these value, we'll get the inertia of cracked section. Okay, and substituting all these values in this first equation, we'll get the strain in the extreme fiber of concrete just before we applied the FRP. So epsilon Bi upon substituting all the values, it will come out to be 0.00031. Okay. Now, the fourth step is the determination of FRP design strain. So we know epsilon Bi now. So epsilon Fd, for before determining the strain in FRP, we need to check what type of failure I will undergo. Whether it will be a debonding failure or whether it will be a FRP rupture. So initially, when we were talking about flexure design, we saw there can be three failures: either concrete crushing, or FRP rupture, or FRP debonding. We need to know which failure mode is governing the design. So epsilon FD, we saw this equation initially. It is given by this relationship. We know FC, compressive strength of concrete. One sheet we are providing, EF we know, TF we know. So substituting all the value epsilon FD, that is the debonding strain in of FRP, it will come out to be 0.009. Okay, and zero point 0.9 times epsilon fu is 0.018. Now since my debonding strain is less than the ultimate strain of FRP, okay, my debonding will control the design and not the FRP rupture, because at a lower strain only debonding is happening, and FRP rupture will happen at more strain. So this means that debonding will happen first and it will govern the design. Okay, so we know now what is the governing factor for us. It is the debonding that is governing the design. Okay, now we need step 5 is the assumption of depth of neutral axis. So we know all the design parameters up till now. Now we need to make an initial assumption of depth of neutral axis. Okay, so that we can check whether the choice of FRP that we have made is good enough or not. Okay, so suppose I am assuming the depth of neutral axis as 0.25 times the total effective depth. Okay, so I'm assuming my depth of neutral axis to be 137.5 mm. Okay, you can make your own assumption also. You can choose 120 mm, you can choose 130 mm. We will see later on how we will check whether the choice is correct or not. So I have assumed the depth as 137.5 mm in my case. Okay, now the next step is to determine that moment capacity. Okay, now before that we need to calculate the stress in FRP also, stress in concrete also, and stress in steel also. So for calculating the stress in FRP, we need to know the effective stress strain in FRP. Okay, in concrete and in steel, the effective strain in FRP we saw from that similar triangle property. It is given by epsilon Fe. So substituting all the values, we know all the other values. So substituting those values, we will get epsilon Fe to be equal to 0.0097 times 0.0097. Now, since this value is again more than 0.009, so it says that my debonding occurs before concrete crushing. Okay, epsilon Fe we calculated by assuming that the strain is compatible with concrete crushing. But since this value is more than epsilon Fd, this means that debonding will happen even before concrete crushing, and thus my strain in FRP at ultimate level is the debonding strain only, and not the strain that we calculated using similar triangle property from concrete crushing. So this is a very important step in design. Okay, you need to always check what failure mode is governing and how it is dictating the property. Okay, now since rebonding is occurring before concrete crushing, so this assumption that we assumed that the ultimate strain in concrete is 0.003, the strain in concrete actually will be less than the ultimate strain value since rebonding is occurring before. So just rearranging this equation, we can calculate the strain in concrete also when the strain in FRP is 0.009 and it will come out to be 0.0027. So we know the strain in FRP, we know the strain in concrete, and we can calculate the strain in steel also from the relationship that we saw earlier. So it will come out to be 0.0083. So we know the strain in all the three materials. Now, once we know the strain, we can determine the effective stress. So, stress is nothing but modulus of elasticity into strain. So, we know all the values. So, we can determine the stress in steel. Okay, and we can determine the stress in FRP. Now, since the stress in steel was coming out to be more than the yield strength, so this shows that the will yield, and hence the stress in steel will be Fy and not more than Fy. Okay, and the stress in FRP, we can just simply multiply EF times epsilon Fe. So you'll get the stress in FRP. Okay, concrete block factors, it is generally assumed as these values. So you this value you can make a note and you can assume before starting also. It is no need for going very deep into how these values are calculated because our focus right now is the calculation of FRP strengthening. Okay, so for now, I am assuming these values. Okay, these per as per codes. Okay, so these assumptions are valid. Okay, now we need to check whether the value of C that we chose initially is correct or not. So how we can check by using the force equilibrium. So we know what is the stress in steel, stress in FRP, and the stress in concrete. Okay, so just by using that earlier equation of force equilibrium, I will calculate the depth of neutral axis again, and it is coming out to be 135.66, which is very close to my choice of depth, that is 137.5 mm. Since this is very close to the choice of my depth, thus the choice of my C value is correct. Okay, and I can proceed ahead. Suppose if this value will be very lower, suppose I would have assumed this value would have come out to be 120 mm. Okay, so what you need to do, you need to make certain changes in your choice of FRP or in your choice of other materials like FRP or FRP width or FRP like the thickness of plate or number of plates you have provided such that you can make a proper match of the depth of neutral axis. Okay, once you verify the depth of neutral axis, okay, the next step is to determine the strength offered by the FRP. So we will calculate the contribution of steel to bending. That is nothing but the equation that we saw earlier, and we'll calculate the contribution of FRP to bending. And by knowing these two values, we can calculate the design flexural strength of the member. Okay, my design flexural strength of member after all the substitution, it is coming out to be 353.45 kilonewton, while my actual movement that I wanted to resist was 91.55 kilonewton only. So we can say that the assumed flexural design can withstand the desired increment in load. So this is after design. Okay, and this was before design. So you can see we are very ahead of what was demanded. Okay, so my assumed section is safe for load increment. Now, one may say that this is not a very sustainable design because I have increased the load to a very higher limit. So, what you can do instead of 2 mm thick CFRP, you can reduce the thickness to suppose 0.2 mm or 0.3 mm. Okay, or suppose 0.5 mm. Okay, assuming this thickness, you can again solve the question and you may get closer to this value. Okay, this will make your design more economical also, and it will make it more close to this value also. Okay, I hope everyone are clear with this question. So I have tried to simplify the solution as much as possible so that you can know what does each step do and what is the importance of each step, and you can remember it also properly which step needs to be followed after what. Okay, any doubt in this question? If there are no doubts, we will move ahead. Okay. So I have given a similar one more question like this to for you to solve on your own. Okay, just follow the same process that we discussed in the last question and try to solve this question also. So this question says there is a original beam of dimensions mentioned as in the question. The original material is reinforced concrete with the concrete strength of 25 MPa, and targeted increase in load is 20% increase than the original capacity. FRP material used is CFRP with tensile strength given and modulus of elasticity given. Okay, FRP strengthening scheme is externally bonded CFRP plate. You need to determine the original capacity of the beam. Okay, the required increase in capacity and the design of FRP retrofitting to meet the increased requirement. Okay, just try and follow all the steps that we have discussed in the previous question and try this question. Okay, if you are not able to get the answer, uh, I will solve the question in the next live session if required. Okay. So I hope this part of flexural strengthening design for FRP is clear to everyone. If yes, we will move ahead now to the next design that is for shear member. Okay, so let's now look at design approach for FRP retrofitted shear member. Okay, so we know that for shear strengthening, FRP is wrapped around the member in three ways, okay, either completely or in a three-sided wrap, U wrap, or as a two-sided wrap. Okay, and these wrapping orientation can also be different. Either it can be perpendicular, okay, or it can be at a particular angle. Okay. So for designing FRP for shear, all these things needs to be considered since each of them will offer a different level of FRP strengthening. And in today's session, we'll see how these factors are included when we are designing a FRP retrofitted shear member. So the aim of shear strengthening is to FRP retrofitted shear member is to evaluate whether the choice in the extent of FRP meets the required shear strengthening demand. Now, there is a basic rule of strengthening that is shown in this equation here. That is, the strength after retrofitting should be more than the required strength. So, VU is the required strength, and VN should be more than the required strength. Okay, that is VN is the strength after retrofitting. Okay, V is the required strength of the member post load increment, and VN is the nominal strength of the member after retrofitting. And phi we know is it is the strength reduction factor to take into account durability and environmental factors. And in case of shear design, we take phi value as 0.75. So it is fixed initially. Okay. Now, when we talk about shear, all three components that is steel, concrete, and FRP will contribute in shear strength. So my VU will be VN will be summation of all three components VC, VS, and VF. And this factor gamma F, it is due to the additional reduction factor of FRP. Okay, which is assumed as 0.95 when it is completely wrapped and 0.85 when it is two-sided or three-sided wrap. Okay, so these values are also fixed and given to us from the code. Okay, so what is known to us? We know how much load is increased on the structure, that is VU. Okay, and what needs to be estimated is the choice of FRB material and extent of retrofitting is sufficient to meet the demand or not. So we need to estimate VN and we need to check whether it is greater than VU or not. Okay, so contribution of steel and concrete to the shear strength we already know from the initial design. What we need to uh, what we need to calculate it is the contribution of FRP to shear strengthening, and it is given by this basic equation as per ASTM code. So it is given by VF is nothing but area of FRP reinforcement into strength of FRP times sine alpha plus cos alpha, which will take into account the angle, okay, at which the FRP is retrofitted. Okay, it can be 90 degree, or it can be at an angle 45 degree. The thickness of FRP, okay, the thickness of the plate that I am installing on the column member, okay, its thickness, and SF, the spacing between the FRP. So suppose I am using FRP strips. So what is the spacing between FRP? Center to center spacing between FRP. Okay, so this is given by SF. So this whole equation dictates the strength contribution of FRP to shear strengthening. Okay, for calculating area of FRP, if it is a rectangular section, it will be given by 2 times N times TF times WF, and if it is a circular section, my AF will be given by this equation. Okay, this is very basic. Okay, now this tensile stress in FRP, it is nothing but strain times the modulus of elasticity. So in case of completely wrapped member, my strain in FRP is given by 0.004, and it should be less than 0.07 times epsilon FU, so that there is rupture in FRP strip. And for two-sided or three-sided bonded FRP, my failure is generally FRP debonding, and it is given by kV times epsilon FU. Okay, and it should be less than 0.004 since there is debonding happening in this case. Okay, so it is generally seen from literatures and previous study that when it is a completely wrapped member, the failure is FRP rupture, and when it is a two-sided, three-sided bonded wrapped member, the failure is generally FRP debonding. Okay, so instead of calculating first what type of failure will happen in this, in case of shear something, we know will be the failure when we are choosing the FRP. Okay, here kV is my bond reduction coefficient for shear that we'll see later on. Okay. Okay, and finally, that shear reinforcement after installation of FRP should dictate this equation as per code. So we'll see later on how this equation comes into action. Okay. Now, for determining the bond reduction factor, the code has again given us this equation, which is K1 times K2 times LE upon 11,900 times EFU. Okay, LE is my active bond length, okay, which is given by this equation, and K1 and K2 are the modification factor. So K1 is the modification factor which takes into account the compressive strength, and K2 is the modification factor which takes into account the wrapping scheme. So if it is a U wrap, my K2 will be given by this equation, and if it is a two-sided wrap, my K2 will be given by this equation. So knowing epsilon FU, K1 and K2 and LE, we can calculate the bond reduction coefficient. And once we calculate the bond reduction coefficient, we can calculate the epsilon Fe value. Okay, once we know the epsilon Fe value, we can calculate the tensile strength stress in FRP. And once we know this value, we can calculate the contribution of FRP to shear strength. Okay, so let's see one numerical here so that we can see how step by step we go in the backward direction from this to this. Okay. So the question says a reinforced concrete beam is located inside a building. Okay, in this question, it is inside a building. It is experiencing an increase in live load capacity by 50%. Okay, assuming that the beam is safe for flexure. Okay, now, in this question, the beam is safe for flexure. The consultant is asked to strengthen the beam for shear using FRP. And for strengthening, the consultant has made the choice of CFRP retrofitting as two strips of two-sided straps. So what he has done, he has taken two strips of two-sided straps. So instead of U strap, there is just two-sided strap that the consultant has initially chosen. Check whether the design of the FRP chosen by the consultant is safe or not for to provide the is safe or not for the incremented load, and if it is not safe, provide an alternative design. Okay, so these are the details given in the question. We know the length of the beam, width of the beam, total depth of the beam, concrete compressive strength we know, steel tensile strength we know, and number of bars and diameter, longitudinal bars. Okay, number of longitudinal bars and its diameter also we know that has been provided. Okay, so this is the live load which is acting initially. Okay, this is the assembly, so I need to provide two-sided plates. Okay, so this is my plate thickness that I have mentioned, 200 mm, and spacing between plate is 300 mm. This is chosen by the consultant. Okay, so this there are total two strips like this, one over the other. So total thickness of each plate is 0.2 times 2. Okay, and tensile strength we know, rupture strain we know, and modulus of elasticity for CFRP we know. Okay, just try to think how we will proceed ahead in this question, and then we will see the solution. In the meantime, if anyone has any doubt regarding shear strengthening using FRP, they can post their queries in the chat box. I will mute myself for a couple of minutes. Okay, let's see the solution now. So, what all things are given to us in the question? We know that the reinforced concrete is located inside a building, okay, beam, and it is experiencing an increase in live load by 50%. And we need to design the beam for shear, okay, shear strengthening using FRP. CFRP is the material that we need to use. Initially, the consultant has chosen two strips, two-sided strips, okay, and two strips for on each side. Okay, and we need to check whether the FRP is safe or not. Okay, and if it is not safe, then we need to provide an alternate design. And these are the properties, and this was the initial beam design. Okay, so again, my step one will be the load calculation so that I can know how much increment in shear force I need to resist for. So dead load again is density times volume. It will come out to be 4.41 Newton per mm square. Live load initially it is given in the question 40 kilonewton per meter, so 40 Newton per mm. And live load finally after 50% increment will be 60 Newton per mm. So unfactored load we can calculate. Okay, unstrengthened load limit this time it will be 0.75 factor instead of 1, since the building is, it is a building in which live load may not be experienced always, so I have taken 0.75 factor. Okay, so unstrengthened load limit is 49.85. Factored load I can again calculate from this relation, 1.2 times dead load plus 1.6 times live load. It will come out to be these values before and after load increment. Based on the load value, I can calculate the shear force for uniformly loaded beam. At the at the edges, the shear force will be maximum, and at the center, my shear force will be minimum. Okay, so this value is nothing but WL by 2. Okay, so I have written here what is the value. Okay, unstrengthened shear force. Okay, without strengthening, what is the shear force that my beams needs to be resist, so that we can ensure that it can undergo retrofitting. So this is this value, and this is the factored shear force. So this is the amount of shear force that is required by the beam to resist after load increment. Okay, so we need to design for this much increment in shear force. Okay, so just for those who don't know how to design a simple RC beam for shear, I have shown the initial calculation also. So as per IS 456, the guideline of shear design, first we determine the tau v, the shear strain in concrete, which is dependent upon the load acting on the concrete. Okay, oh, just a second, my mouse is not working. So here you can see in this question, first I determined the tau v value, which is nothing but VU upon BD. So VU we know it is 173.23 due to the load acting on the beam. Okay, factored load on the beam. So VU upon BD we can calculate. We will get the tau V. So this much amount of shear force I need from reinforced concrete. Now I know the area of longitudinal reinforcement. Okay, and I know the grade of concrete. So based on these two values, there is a table given in IS 456 that you can refer to, and it will give you the how much shear strength the concrete will provide. That is denoted by tau c. And we also know the maximum shear strength that the concrete can resist, that is tau c max. Okay, since my load since my shear force that I want to resist from reinforced concrete is more than tau c, I need to provide some additional shear reinforcement. And those shear, the stress taken by those shear reinforcement is denoted by Vs, and it is calculated by this equation, tau v minus tau c times Bd. Okay. Once we know how much shear force we need to resist, I will make an initial choice of stirrups. So I have chosen 8 mm double leg diameter stirrups, and using the equation 0.87 times Fy times ASV times D upon SV, I will calculate the spacing between the stirrup, and it will come out to be 300 mm. Okay, so knowing the amount of stirrup shear reinforcement I have provided, I will get to know what is the shear strength of of my existing reinforced concrete, due to concrete, and what is the contribution of steel in that shear strength. Okay, so these two are the contributions. Now, if you will add this 107.2 plus 66.51, and you if you will multiply the load decrement factor of 0.75 that we saw initially, okay, this value should be greater than the unstrengthened load limit, unstrengthened shear force limit, that was 124.625. Okay, if this is true, then only we can choose retrofitting. If it is not true, then it is better to demolish the structure. So upon doing this calculation, we will get a value of 130.28. Okay, since 130.2 is greater than 124.625, I am safe for retrofitting. So this is my step one to check whether my structure is safe for undergoing retrofitting or not. Okay, and in this slide, I have tried to summarize IS 456 design of shear reinforcement also for those who are not clear or those who may forget the design. Okay. Now, how much I need to strengthen? I need to strengthen so that it can resist this shear, this amount of shear. Okay, so let's start. So step one will be to make the initial assumptions. So I have taken two plies of CFRP as external shear reinforcement attached at two-sided strip that was chosen by the consultant. So the effective depth is 550 mm as we saw on the last question. Width of each sheet is given to us. Spacing between each sheet is given to us. Now, how many sheets I can provide on one side? So it is nothing but number of strips. Suppose I am assuming n. Okay. So in between two strips, my total spacing is 300 mm, center to center. Okay. So since this length is 200, so this will come out to be 100 mm. Okay, 300 minus 100 from here, minus 100 from here. So clear spacing between strip is 100 mm. My total length of beam is 5000. If I remove from the side two clear spacings, so 5000 minus 200 is 4800. So there are n strips and there are n spacing between them. So 5000 minus 200 will be nothing but it should be occupied by number of strips and number of spacing. So n times 300. 200 for each strip and 100 for each spacing. So upon solving, you will get it. There are 16 strips that we can provide on each side. Okay. So my total FRP strip length on each side will become 3200 mm. Okay. I hope this calculation is clear to you. Okay. If not, just try to listen to this lecture again and try to understand this diagram. It will be very clear to you. It is very simple. Okay, now I know the initial assumptions. Step 2 is to determine the material degradation parameter. So since it is an interior member, my environmental factor will be 0.95. So my FFU and epsilon FU, it will be 950 MPa and 0.0019. Okay, this we saw in the last question also, so I won't elaborate further. Okay. Now I need to determine the effective strain level in FRP. Okay, so that I can calculate the stress in FRP. The strain for two-sided strip is given by this equation we saw earlier. And in this equation, I need to calculate the bond reduction factor Kv, which is given by this equation K1 K2 Le upon 11,900 times epsilon Fu. Okay, Le is the effective bond length, which is given by this equation. Here we know N, we know TF, we know EF, so we can calculate Le. Le will come out to be 100.33 mm. K1 is dependent upon the concrete strength that we know. So it will come out to be 7.1.07, and K2 it governs the effectiveness of wrapping. So it is given by this equation we saw earlier as per ACI code, and it will come out to be 0.36635. So substituting all these value, my KV will come out to be 0.301. It is less than 0.75, so I will go with 0.301 value also only. And once I know KV, I know epsilon FU 0.0019. 0.019, so I can calculate the effective strain in FRP, and it will be 0.301 times 0.019, so it will be 0.0057. Since this value is greater than 0.004, my epsilon Fe will be 0.004 only, and this shows that instead of debonding that should happen in uh, two-sided strip here. Instead of debonding, FRP rupture is governing the failure. Okay, because for rupture, we saw earlier in the equation the strain is 0.004. So here FRP rupture will happen before debonding. Okay, this also you can conclude from this value. Now we know the strain and we know the area of FRP reinforcement. So I can calculate the effective stress in FRP, epsilon Fe times EF. Okay, it will come out to be 0.12 kilonewton per millimeter cube. Okay, so the shear contribution of CFRP strip, okay, it will be given by this equation that we saw earlier. So substituting all the values, alpha is 90. Okay, so sine alpha is 1, cos alpha is the 0, so 1 plus 0 is 1. Okay, so here factor will be 1, it won't matter to us. AFE, substituting all the values, I will get my shear contribution due to CFRP two-sided strap as 35.2 kilonewton. Okay, now once we know the shear contribution due to FRP strip, we can calculate the design shear strength. Okay, so my design shear strength will be Vs plus Vc plus Vf. Okay, we know this value initially from design, and we saw today also how we calculate, and we know Vf also. So adding all the values and multiplying the bond reduction, load reduction factor, I can calculate the design nominal shear strength after FRP retrofitting. Okay, and it is coming out to be 152.73 kilonewton, which is very less than what I required. Okay, so the choice that the consultant made right now, it is incorrect. It won't be sufficient. So I need to redesign. So how I can redesign? So instead of 2 thick FRP, I am choosing 1 thick FRP and 4 strips of U strap CFRP. So instead of two-sided strip, I am going with a U strip. Okay, and instead of 2 strips, I am choosing 4 strips of 1 thick FRP. Now, making these assumption, I will again calculate the value of VF as the step as per the steps I showed here. Okay, and now my VF will come out to be 264 kilonewton. With this VF, if I will calculate the design shear strength again, it will come out to be 298.58 kilonewton, which is greater than VU, what I needed to resist. So these choices enough for FRP retrofitting for shear design. Okay, and this I will finalize. Uh, any doubt in the solution? So initially we designed the reinforced concrete. We calculated what is the shear strength of concrete, what is the shear strength of steel. We checked whether the initial concrete is safe for undergoing retrofitting or not. Then we made our initial assumptions of CFRP. Then we determined the material degradation factor. We estimated the effective strain in FRP. We calculated the shear strength that is offered by the FRP. Okay, by determining the shear strength of FRP and then determining the net shear strength, we determined the net shear strength offered by the section where we took into account both concrete, steel, and FRP, and we checked whether it was sufficient or not. If it is not sufficient, we chose an alternate design and we again do the redesigning and we verify the design. Okay, any doubt in this part? Shear design of FRP? If no doubts, we'll proceed ahead. It is important for you guys to go through the lecture once again so that you can understand these tips more properly. I've tried to simplify each step as much as possible so that you can remember it also properly. So you need to remember first you need to determine strain, then you need to determine stress, and then you need to determine the strength. In both the cases we saw it was a similar procedure: strain, then stress, and then the strength. Okay. So let's move ahead. Finally, let's talk about design approach of FRP retrofitted axial member. So when we are talking about axial strengthening of FRP, we mean FRP confinement of existing columns. Okay. Now, what FRP confinement does? Okay, when FRP confinement act, okay, It acts when the confining effect is experienced by column under axial loading after the concrete has cracked and it begins to dilate. So, unlike other cases, here it is not like both my existing column and FRP are acting together from the start. FRPs are in passive state. Okay, it won't give any contribution to axial strength. Okay, initially it won't contribute. But when my existing concrete will fail, my FRP will give the confining pressure to the existing column and it will strengthen the column. Okay, so this is the crux of FRP confinement. It acts after the concrete has cracked and begins to dilate. Okay, and the effectiveness of confinement, as we know, will depend upon the concrete strength, the concrete dimension, the elastic modulus and ultimate strain of FRP, and the thickness of FRP wrapping. Okay. So the aim of FRP retrofitted axial member is to evaluate whether the choice and extent of FRP retrofitting design meets the requirement of axial strengthening or not. Now here there is a basic rule of strengthening that is shown in this equation. Okay, that is the strength after retrofitting should be more than the required strength of the member. So my PN is the nominal strength of member after retrofitting. PU is the strength of the member post load increment. Okay, so after increment of load, how much axial strength the member needs to resist, that is denoted by PU, and alpha phi is my strength reduction factor. Okay, so in case of spiral reinforcement, my PN is calculated by this equation. Okay, where I have taken contribution of FRP also and the contribution of existing RC also. Okay, and if there are tie reinforcement, my PN value is given by this equation. Okay, so this is as per ACI guideline, ACI 318 guideline. Okay, so FCC dash is the compressive strength of confined concrete. Okay, and it is applicable when my eccentricity is zero. So these all equation are valid when I have a axially loaded member and not eccentrically loaded member. Okay, now, how to decide the value of strength reduction factor? So it depends upon the strain at nominal strength and the type of the member. So you can see epsilon T. Epsilon T is the tensile strain in extreme tension steel at nominal strength, and epsilon Ty is the tensile strain at extreme tension steel used to determine the compression control section. So knowing these two values and how these values are related to each other, we can calculate the strength reduction factor. If it is a spiral reinforcement, we will use this equation, and if it is a tie reinforcement, we'll use these values. Okay, and again it is a linear value. One is varying between 0.75 to zero point 0.9, and other one is varying between 0.65 to zero point 0.9. Okay, and these values are decided as per the codal guidelines of ACA 318. Okay, now in axial loading of column, we discussed that the action of confinement starts when the existing infrastructure fails to take load. Okay, so the behavior of retrofitting column is a bilinear relationship. Okay, so why we say it as bilinear? Because initially my concrete is taking the axial load, and once my concrete fails, my FRP is taking the axial load. Okay, so this is a bilinear stress strain behavior. Okay, now a confined concrete bilinear stress strain behavior is represented by two curves. The first one is the parabolic curve, which governs the concrete behavior, and second one is the linear curve, which governs the FRP behavior. So first curve represent the unconfined concrete, where FC dash means the unconfined compressive strength of concrete, and epsilon C dash means the compressive strength in unconfined concrete. That is very clear to us. Okay. Then there is a transition in between from unconfined to confined state. Okay, where cracking concrete starts. Okay, here epsilon T dash denotes the 10 transition strain of concrete, and finally we reach the second curve, which is the confined concrete, where FRP confinement has taken guard after concrete cracking. Okay, here FCC dash means the maximum confined concrete compressive strain. Epsilon CCU means the ultimate strain in confined concrete. So our aim is to determine all these values so that we can design a FRP retrofitted axial member. Okay, I will make this correction here. This is axial member. Here also axial, and here also axial. Okay. Now, here in this bilinear relationship that we just discussed, it's important to determine each parameter. Okay. So the strength of unconfined concrete, it can be determined by two relationship. One is for the parabolic section. The first relationship that you see here, it is for the parabolic section. Okay, and the second relationship is for the linear section. Okay. Additionally, it is important that epsilon Cmax should be less than epsilon CCU should be less than 0.001. This is to ensure that concrete rupture within FRP is not too critical. Okay. So for that, this condition is applied. Okay. For linear region, my E2 is given by this equation. That is nothing but stress upon strain. So stress is nothing but difference between these two values. Okay. So this uh, the slope of this curve is E2 and it is nothing but stress upon strain. Okay. And Et dash, the transition strain is given by this value. Okay. And all these values hold true when FC dash is not more than 70 MPa. Okay. So when my initial compressive strength of concrete is less than 70 MPa, then only all these relationships hold true. Okay. Additionally, I can determine the confined compressive strength of concrete once I know FC dash, and so I can calculate the confined compressive strength of concrete by this relationship FC dash plus gamma F, FC dash plus gamma F times 3.3 times Ka times FL. So here FL is the maximum lateral confining pressure, which will provide the confining strength to concrete. Okay, and it is given by this equation. It totally depends upon the confinement that is provided by the FRP. Okay, and effective strain in FRP, it is given by this equation. Okay, Ke times the epsilon Fu. Here I know I need effective strain, so strain I will calculate from this equation. Epsilon Fu I will know from the material property, and K is the efficiency due to strain reduction. It is the strain reduction factor. Okay, and Ka that I used here, it is the efficiency due to geometry. Okay, we will see later on how K is calculated, and gamma F, its value is fixed as 0.95. It is a strength reduction factor. Okay, and the maximum strain epsilon CCU, it is determined by this equation, and it should be less than 0.01. So to prevent excessive cracking in concrete, and to achieve minimum lateral level of confinement, we need to follow this relationship also. Okay, here KB is again the efficiency factor due to geometry. Okay, for circular section, both K and KB is equal to 1. However, for rectangular section, K and KB are less than 1. So we know this from previous discussion also. We saw that in case of column confinement, corner radius plays a critical role, and since if there is sharp edges at the corner, it can lead to stress concentration and ineffective wrapping. So just to take into account those cases, we have K and KB, the efficiency factor. Okay. To determine this efficiency factor, I first need to determine D, which is the effective radius, effective diameter, which is nothing but b under root of b square plus h square. And from those, we can determine the K and KB value. Okay, here A is the effective confined area of concrete, and AC is the concrete in compression member. And the ratio of AE by AC is governed by this equation. Okay, where RC is the corner radius and rho J is the longitudinal steam reinforcement ratio. So practically, when you are solving a question, you need to remember such some of these relationships. Okay, each of the relationship has been developed so that all the factors that can affect the flexural strengthening due to FRP can be taken into account properly. Okay, so we need to determine AE by AC first. From that, we can determine the efficiency factor due to geometry. Once we know the efficiency factor, we can determine ECCU value, epsilon CCU value, and FCC dash value. And once we know these values, we can determine whether the axial member is properly retrofitted or not. Okay, so just to explain you the application of these uh, equation, let's see one numerical for axial strengthening also. So I will just show you the question. So this is the question. Okay, so the question says we have a square column of sides 300 supporting a bridge deck, and it requires an increment of 75% in live load, in axial capacity, in axial load carrying capacity. Okay, with the current concrete and the reinforcement detailing, the axial strength is insufficient to meet the demand. So strengthening is required, and for strengthening we are using CFRP for confining the concrete as external wrapping. So we are asked to design the CFRP wrapping. Initial axial load on the column is given. It is 1000 kilonewton, and you need to design the column just to meet the requirement. Okay. So after 75% increment, we need to check whether my FRP is just meeting the requirement or not. So these are the details: length, breadth, width, concrete compressive strength, steel tensile strength, and corner radius. Okay, corner radius like this. Okay, and these are the details of CFRP. Okay, just try to think how we will proceed ahead in this question. I will wait for a couple of minutes and then we'll see the solution. By the time, if you have any doubt regarding axial strengthening, you can ask. Okay, let's see the solution now. So we know the initial condition. Okay, the column dimensions we know, uh, uh, compressive strength of concrete we know, steel strength we know, and the corner radius we know. We know the detail of CFRP, and we know how much increment in axial load is happening. So initial axial load was 1000 kilonewton. Okay. So existing axial reinforcement of concrete we can calculate. Okay. So this is as per IS 456 guideline. Just for those who don't know how to design for axial, for how to do axial design for RC column, I have just mentioned it here. Okay, so I'm assuming the effective length is 0.8 times L, which is the case when the column is held in position at both end and restrained from rotation. So by L effective, we can calculate L effective by V. It is 8, which is less than 12. So hence it is a axially loaded short column. Okay, so for at 2.002 strain level for steel, okay, I will calculate the PU by the relationship given in IS 456. Okay, so my PU is given to us, factored PU, it is 1000 times 1.5. We know the area of concrete, we know FCK, FY, so I can calculate ASC. Okay, this is the area of steel under compression. Once I know the total area of steel under compression that I need, I can design for diameter that I require. So assuming I am using 16 dia bar, I will be requiring 12 numbers of 16 dia bar so that I can fulfill this condition. Okay. Once I know how much steel reinforcement I have provided, I can calculate the percentage of steel reinforcement. So it will come out to be 2.34%. So PN without FRP was say 1500 kilonewton, and PN required is 50% is for 75% load increment. So it will come out to be 2625 kilonewton. So this is for what we need to design. Okay. So first step is to estimate the design properties of CFRP. Again, since the column is an outside column, my environmental factor will be 0.85 instead of 0.95. So FFU and epsilon FU I will calculate. Okay. Now determining the required compressive strength of confined concrete. So I know AST, I know FY. Okay, I know how much increment is happening in the load that I want to resist. I just need to know how much FRP needs to contribute to increase this load. Okay, so by this initial equation, knowing all the other value, I will calculate the FCC dash. That is the required compressive strength of confined concrete. Okay, so substituting all the values, I will get FCC dash value as 29.23. So this is the compressive strength that I require from the confined concrete. Now, to get this compressive strength, there are two factors that contribute. One is the concrete and one is the FRP that I have wrapped. Okay, wrapped around. So now I need to determine the required confining pressure which can cause this amount of confining stress. Okay, that is FL. Okay, so we know FCC dash we calculated just in the previous slide. FC dash we know, I need to calculate FL. Okay, before calculating FL, I need to calculate K also, that the bond reduction factor due to geometry. So K is nothing but this by given by this equation, and AE by AC we saw the relationship that governs AE by AC. So substituting all the values, we know B, we know H, we know RC, we know AG, that is 2.34 percentage of longitudinal reinforcement. Okay, and this is, sorry, gross area we know of concrete 300 into 300, and rho g we know. So substituting all the values, we will get AE by AC, that will come out to be 0.537, and by this we can calculate Ka. Okay, once we know Ka, we can calculate FL. Okay, so just rearranging this equation, I will get the confining pressure due to safe RP. Okay, and this should be more than the minimum confinement ratio. So FL by FC dash we will calculate. It is coming out to be 0.101, which is greater than 0.08. So we are safe for design. Okay, we are safe. Now, I need to determine how many number of piles of CFRP I am required to get this much amount of confining pressure. So lateral confining pressure is given by this equation. Okay. Now I know the value of FL, I know EF, I know TF, I know epsilon FE. Epsilon FE I need to calculate and I need to calculate D. So D is nothing but under root of B square plus H square. So substituting the values, it will come out to be this value. And epsilon Fe is nothing but Ke times epsilon Fu. Epsilon Fu we know, and Ke also we know. Okay, we calculated it here. Ke value is a constant that we assume that was given initially in the question in the slide that we discussed. Okay, here you can see K is a strain efficiency factor which is range from 0.55 to 0.61. For this question, I have assumed the strain efficiency factor as 0.55. Okay, so substituting all the values, I can get the number of piles of CFRP that I need to create this much amount of confining pressure. So it will come out to be 0.3.39. So I will take 4 sheets. Therefore, 4 sheets of CFRP is needed to be wrapped around for taking the additional load. Now, as a safety check, I need to check whether the ultimate strain in concrete is within limit or not. If it is greater than 0.01, what will happen? My concrete will failure will be very severe. That I don't want. So just calculating epsilon CCU from the relationship that we saw, we know all the values here. Okay, just substituting all the values, you will get epsilon CCU as 0.0027, which is less than 0.01. Thus, my choice of CFRP and the number of CFRP strips that I have chosen is safe for design. Okay, so this is the design procedure for axial strengthening of FRP. Okay, so what we do initially, we determine how much compressive strength of confining concrete we need. Okay, for getting this much amount of strength, how much confining pressure I need from CFRP wrapping, and for getting this much amount of confining pressure from CFRP wrapping, how many number of CFRP plies I need to provide. CFRP plies or CFRP sheets you can write. And we need to check later on whether the ultimate strain of confined concrete is under the acceptable limit or not. Okay, any doubt in this question, design of axial strengthening? Any doubt in the discussion that we had today regarding flexure or shear or axial? So these questions are like, if you are looking at these solutions for the first time, it will seem to be very confusing. You won't be able to memorize, or you will be a lot confused. But just try to go through this lecture once again. Just try to solve that question on your own. Remember the steps and try to execute those steps on your own. Once you will execute the steps on your own, it will become very easy for you, and more you will practice, the more easy it will become. So in the NPTEL assignments, some similar questions are given, but those are very simple. If you are able to solve these three questions on your own, once again, all the questions of NPTEL and maybe later on in the exam will be very easy for you. Okay, and it will like help you further on also in your actual field application or maybe in future. Okay. If there are no doubts, we'll conclude the session. So in this session, any doubt? Anyone has unmuted?
Hello?
Yes.
Hello? Any reference textbook?
Your voice is not clear. Can you just type your query in the chat box?
I'm having difficulty trying to type. But can you hear me now?
Just write in the chat box. No, I'm not able to understand.
Okay.
By the time he is asking his query, let's see the what we have looked in this session. So the
Right.
session we talked about the design of FRP retrofitted member based on the requirement of strengthening. We first talked about FRP retrofitted flexure member. We saw a brief overview of design procedure and we solved a numerical. Similarly, we saw shear members, a brief overview of design and numerical. And for FRP retrofitted axial member, we also saw the design procedure and the numerical. Okay, so this was all that we talked in the week 7 content of the course.